So today we will start with the simple harmonic motion. Okay. So before we start with the simple harmonic motion, let us have a look at a few points regarding motion in a straight line, because the simple harmonic motion is a specific type of motion in a straight line. Straight line means it is a one-dimensional motion. Okay. So we will consider a particle which is moving in a straight line. So suppose consider figure 1. Okay, so what can happen in a straight line, suppose O is a fixed point and our particle at any instant is at the point P. Okay, so under the under the action of an external force, the particle will move. Okay. Achha. When the particle is moving, we are considering any specific instance, and at any time t, our particle is at point P, and later our particle has started from the point A. Okay. So now, depending on the external force, that means the external force can be of two types, either attractive force or repulsive force. Achha. O is considered to be the point, fixed point, and often referred to as the center of force. Okay. So it may happen that the force is in this direction. That means what? It is pulling the particle. Say suppose the particle initially or at time t equal to 0 was at A. The force F1x, that means it is a function of the distance from O, is directed towards the point O. So it is actually attracting the particle towards the point O in figure 1. Just the opposite is happening in figure 2, where the particle is repulsed or is thrown away or pushed away from the point O. So it is a repulsive force. This is an attractive force, this is a repulsive force. Okay, so whenever we are talking about motion in a straight line, either first and foremost of all, there will be an external force. As long as there is an external force, the particle will be moving, and then only we can find out the velocity, the distance covered, the velocity, the acceleration, and like some other parameters. Okay, so first and foremost of all, the fundamental thing is there will be an external force. And now when there is an external force, what is the nature of the external force? Whether it is attracting the particle towards the fixed point, or it is just throwing away or pushing away the particle from the fixed point. Okay, so whenever we do any sort of problem regarding motion in a straight line, that is one dimensional motion, as you can see, what we are repeatedly saying ki the particle is moving along this straight line. So when the particle is moving along this straight line, no matter in which direction, either in this direction or in this direction, what is changing with time? The distance of the particle from this fixed point is changing with time. So there is only one parameter which is varying with time. So it is a one dimensional motion. Okay. Now we are taking into consideration motion taking place in along a straight line, so one dimensional motion. And whenever we do this type of problems, we will see later we have to mention some specific properties or some specific notations we have to mention first. Okay, first and foremost of all, whenever we are talking about any motion, whenever we are trying to frame the or we are trying to solve the problem related to this motion of the particle, the first and foremost of thing is that we have to fix our reference frame. Okay, that means we have to consider a fixed point as the origin, and we have to consider a fixed line as our initial line along which the distance will be measured, and the fixed point will be the point from which the distance will be measured. So two things: one, a fixed point we need from which the distance will be measured, how far it is the particle is going away from the point, or how closer it is coming towards the point. That is the thing we have to keep in mind. So we need a fixed point, that means we need the origin, and we need an initial line. As it is one dimensional, so in one dimension we as if we need the x-axis. So we need to fix the origin and we need to fix the x-axis. So whatever problem you do, whether it is a simple harmonic motion or it is a motion under inverse square law or under any formula or any formulation of on the external force, two things we have to keep in mind. We have to first fix the what will be our origin for that specific problem and what will be our initial line for the specific problem. This is very important, because depending on this, the whole strategy will be changing. The solution after all may be coming out the same. Obviously, it doesn't depend on the strategy, but whatever reference frame we are working with, we have to fix that in the very beginning. And once we fix that, then you move along with whatever problem is given to us. Okay, so that's why O fixed point is to be considered and towards O or moving away from O, it depends on whatever external force we are considering. Say in figure 1 it is moving towards O, or in figure 2 it is moving away from O. This, as I already said, it depends on the external force. And the, as I have already said, the external force is a function of x, that is the distance of the particle at any time t from O. So we will see, it will become more clear once we do some specific problems. Whenever the what is the external force? Say suppose there is a particle just lying on a plane, or just consider a particle lying on a straight line, and all of a sudden is given a just blow. Okay, it is given a blow. Just you just take a ball and you just give it a push. Okay, so as soon as you push it, your push is acting as the external force, and the ball is a particle which was initially at rest, and as you push it or give it a blow, it will start moving. Okay, so once you start moving, the whole scenario comes into consideration. What is the external force, how is it varying with time, how, what is the velocity of the particle, that means the ball moving here. Okay, so everything we have to consider here. So the external force in general is a function of the distance. That's why I have mentioned f1x or f2x. It depends on the distance from the fixed point. Okay, now it may, this f1x and f2x, what will be the specific form? It depends on this problem which is given. Okay, one type of specific form is given by the simple harmonic motion itself. Okay, where the this f1x is just directly proportional to x, that means it is of the form mu x. We will see in later, just in a few moments. Okay, so this is the general form, you may say. The external force is the function of x. Okay, so now once we have all this information in our hand, the equation of motion is the foremost important thing to solve any particle dynamics problem. Okay, so equation of motion means what? This is what? d2x dt2. d2x dt2 means the acceleration of the particle. That means, see, this is change of x with respect to t gives you velocity, so this dx dt, and again the change in velocity with respect to t gives you acceleration. Okay, so if I consider here, actually we are applying Newton's second law of motion. If I consider a unit mass particle, that is m equals to 1, then m here is 1, so d2x dt2 equals to what? The external force. This is a property of the particle itself, because it is dealing with the change in the position of x, or change in the position of change in the velocity of the body with respect to time, the left hand side. And right hand side is the external source. That means whatever blow we are giving, whatever external force we are applying. So this is the property of the particle which is moving, and this is the external force. Using Newton's second law of motion, we can get an equal to, that is whatever the external force is acting on the body is equivalent to the rate of change of velocity. Okay, that's the acceleration of the body. Okay, so this is the main equation of motion. Okay, now just look here, equation 1, what is that we are doing here? You have put here minus. Why we have suddenly put minus, and whereas in equation 2 there is no minus, that means plus we have taken. Okay, so there is a change in sign. Why this change in sign is coming? That means between left hand side and the right hand side there is either a match or a mismatch of direction. First of all, let us consider the left hand side. Okay, so for the left hand side, what we are measuring, actually we are measuring the change in dx dt with respect to t. That means after all we are measuring the change, some sort of change in x with respect to t. Because if dx dt is changing with t, that means definitely the distance is also changing with t. Okay, so this is increasing if x is increasing with t, and this is decreasing if x is decreasing with t. So if I consider the figure, now you see why we, as we said earlier, ki fixing the initial line and the fixing the fixed point is very important. Now you see we have considered this as our initial line, that means x is increasing in this direction. So if x is increasing in the direction, this is the direction where with time x is going on increasing. Okay, so this is the direction of d2x dt2 increasing along ox. d2x dt2 is increasing. One typo, let me mention here, I should have put here a capital X so as to indicate the initial line. Okay, just consider a capital X here, so that ox is the initial line. So d2x dt2 is increasing along ox. But in figure 1, what is the direction of the external force? It is just in the opposite direction, that means along XO. So x d2 as d2 is increasing along OX, whereas F1x is just acting in opposite direction. So there is a mismatch in direction. D2 as d2 increasing in this direction and F1x is acting in the opposite direction. So there is a mismatch. To adjust this mismatch, we have to put a minus. So the minus is coming here. So what we can say in just one word key, that whenever we are dealing with an attractive force, that means whenever the particle is moving towards or particle is attracted towards a fixed point, then you have to put a minus here. Okay, and just in the opposite, in figure 2, you see d2 as dt2 is obviously increasing in the direction of x increasing, that is quite obvious. But here the external force is in the direction of OX only, that means in the increasing direction only. So there is no mismatch of the direction between d2 as dt2 increasing and between the external force. So between left hand side and right hand side there is no mismatch in direction, so there is no minus sign required here. So this is the case, that means plus will be coming when we are dealing with a repulsive force. Okay, so whenever you are doing any sum, just you have to keep this in mind whenever we start with the motion or equation of motion for doing any type of particle dynamics problem. First and foremost of all, you have to specify all these specifications, what are initial line, what is your fixed point. That is the first and foremost important thing. And before that also, you have to give the figure, a proper figure, not just arbitrary figure you give and some figure you are giving which doesn't match with your writing. That will obviously give you error. Okay, and definitely marks will be deducted for that. So you have to give a proper figure, as much specifications as you can mention, you have to show it in the figure, such as the external force, the fixed point, the initial line, and many other. It depends on the problem. I cannot say it all at this single moment. Okay, so first and foremost of all, you have to give a very specific or appropriate figure. Then you have to mention the initial line, the fixed point, and in case you are working with 2D, we will see later, you have to mention the x-axis, y-axis, and everything like that. That means you have to fix the reference frame in one word. Okay, and then you have to be very specific about the equation of motion. You have to write it, and you have to justify. In case you put a minus, you have to justify why you are putting a minus. Okay, and even if you are not putting the minus, you have to justify why you are not putting it. Okay, so this is the first thing. And then while you are writing this, we will show also ki what is x. X is the running variable. What is t? T is the running time. That means at any instant of time, you have to mention ki at any instant of time, the position of the particle is at point P such that OP is equals to x. That means here, okay, consider it is at any instant of time. See, if the particle is moving starting from say A, so A is the initial position. If it is moving, we do not know at we do not know at which point it will be at any time. Okay, so we are just arbitrarily picking any point within this range. So P is that arbitrary point. So if P is an arbitrary point, so its position or this distance from O should be also arbitrary. So we are just using this x, the running variable, to denote its distance. And you have to do it in each and every problem, because this is also important. What is x? Is it fixed or is it just just a running variable? You have to mention that. Okay. So now all these are clear. Let us now go into the thing which we will discuss today, that is a simple harmonic motion. Okay, so simple harmonic motion, as I already said, is a particular example of this type of 1D motion, that is one dimensional motion, where there is some specification ki f1x is mu x. Actually f1x is mu x and it is of attractive type, that means it falls in this category, equation 1 category. Okay, let us go into it and see it on our own. Acha. Let me just discuss it here only, though we will just come it along once we do some specific problem. That is another problem we have to keep in mind while we are doing it. Suppose we started with the equation of motion, that means that we started with the acceleration, right? d2 x d2. Then once we integrate for one time, we will get dx dt. Okay, so once you get dx dt, in some cases and in fact most of the cases, you will get something like this: dx dt whole square equals to actually f3x, if I say, or actually if you say f3x whole square, it is better to say f3x whole square according to what I have written in the next line. So say dx dt whole square equal to f3x whole square. Suppose by integrating once, d2 x d2 equals to whatever is given. we get this thing. That means by equating, integrating, not equating, sorry, by integrating this one or this one, we are getting this one. X3x whole square. This is the typo here, x3x whole square. Okay. So what is dxdt whole square? Dxdt, first and foremost of all, it is the velocity of the particle. Again, you see, x is changing with t. So x is what the position of the particle. It is changing with t. So it is something, a property, inherent property of the particle. Okay. And on the right hand side, it is coming from the external source, because here initially it was F1x, that means the external force which was given, and then by integrating, but that means by doing some operation, we have obtained this. So it is obtained from the right hand side, integrating the right hand side only, right? So right hand side was an external source property. So once we integrate also, it remains external source property only. So on the right left hand side, we are dealing with the particles property. On the right hand side is the external sources property. Okay, so whatever, dxdt whole square equal to say f3x whole square. So well, now if I want to find out dxdt, we know it can be plus or it can be minus. Now which sign we have to take, it depends on the problem given. Again, how we decide whether we have to take the plus or we have to take the minus, again we have to consider the reference frame we have given here. So what is the reference frame we have given here? As I already said, x is increasing in the direction, so along with time x will be increasing in the direction only. That's why dx dt is increasing in the direction, d2 is dt2 is also increasing in the direction. So as dx dt is increasing in the direction, so this is the direction of the LHS, that means left hand side of this equation increasing. Now it depends on the problem, key if a velocity or the particle is moving in such a way that, suppose in this figure, suppose let us consider figure 1 only, an external force, suppose the ball was kept here and you just pushed it in this direction. Okay, so as you push it in this direction, it will move in this direction. So velocity of the particle due to this push is in this direction. So the velocity of the particles direction is in along xo. Okay, so it is in the direction opposite to ox. That means dx dt is increasing in this direction, but due to the blow which you have given, your particle is moving in this direction. That means due to the blow, the velocity is in this direction. So again a mismatch is coming. So in that case, you have to put a minus. This one. See, if particle moves towards O and hence velocity of the particle is directed along PO. PO means this one. P is in the instantaneous position you are taking along PO. Okay, in this case you have to put a minus. Just in the opposite case, you do not have to put a minus, because in that case there is no mismatch. dxdt is increasing in this direction and your particle is also moving in this direction. That means suppose your particle initially was at a dash and you have pushed it in this direction. Okay, so accordingly your particle is moving in this direction and dxdt is also increasing in this direction. So there is no mismatch in the directions of left hand side and right hand side of this equation. So we will put a plus in that case. So this is another very important or crucial factor you have to keep in mind while doing this type of problems. Okay. Now let us go to the formal definition of a simple harmonic motion. So this is the definition: a particle is said to execute a simple harmonic motion if it moves in a straight line such that its acceleration is always directed towards a fixed point on it and is proportional to the distance of the particle from the fixed point. So two things we have to keep in mind here. First and foremost of all, it is one dimensional motion. As you can see, it moves in a straight line. So no question of two parameters, only one parameter will be ruling. Only the distance from fixed point is to be kept in mind. And what are the two crucial factors? First is the acceleration is always directed towards the fixed point. So if this is a figure, this is the fixed point O, this is the starting point, this is the position of the particle at any time. How is the particle moving under the external force? So what is the external force acting? The external force is acting in this direction. Okay, if your particle is on this half, that is in the OA half or OX half, or if your particle is in the OX dash half, then again it is moving in this direction. So these are arrow signs which indicate the acceleration's direction. So acceleration is always directed towards the fixed point. O is the fixed point, and is proportional to the distance of the particle from the fixed point. So whenever we want to specify a vector, we need mainly two things: the magnitude and the direction. So direction we are specified just now. And what about the magnitude? It is proportional to the distance of the particle from the fixed point. Okay, so mu is the proportionality constant, so mu x. Okay, so in this case it is mu x, and in this case, as it is ox is the initial line, so ox dash is just the negative of the initial line, so mu into minus x in that case. Okay, Achha. Now, so if this is our case of simplifying motion, then what we have to do if we want to solve it, we have to frame the equation of motion as I already said. So if you consider here they are considering two parts. Once they are considering this ox part, here mu x, and in the ox dash part it is minus mu x, because along this there is a negative coordinate, and along this is a positive coordinate, just as our negative axis, positive x axis and the negative x axis, just like that it is playing the role. Okay, so if I consider towards along ox, okay, so on the left hand side, sorry, not on the left hand side, but the right hand side, what will be the equation of motion? d2x dt2 equals to minus mu x. Why minus? Because it is directed towards O, but your d2x dt2 is increasing in this direction. That means what we have already said just now. Okay, d2x dt2 equals to minus mu x. Okay, and here on the right hand side, sorry, on the left hand side, what will be the role? It is moving along x increasing only, because you are moving in this direction, and it is the direction of the d2 d2 increasing. Okay, but here minus will be coming because of this negative coordinate. So ultimately you will get the same equation of motion, that is d2 dt2 equals to mu into op dash. Okay, but op dash itself is negative, so mu into minus x, so equals to minus mu x. Okay, so you see equation 1, equation 2 are the same. So it doesn't matter whether we consider this or this, we just consider any of this and then we proceed with our integration. Okay, so we consider this is our equation of motion. So to solve the equation of motion, what we do here, we use this relation d2 dt2 equals to v dv dx. I have shown you here, or obviously you can sort it out on your own how d2 dt2 turns out to be this one. Okay, so v dv dx equals to minus v x. Okay, so just you have to follow the standard rule, nothing else. You have to integrate. Once you integrate, you get this thing where c is an arbitrary constant. I repeat again here, keep whenever you do integration, please in the next line only you have to mention the arbitrary constant. Not that you put a c here and at the very end you mention that it is an arbitrary constant. It won't do. Or you integrate here and put the arbitrary constant after a few steps, that will also not do. As soon as you say you are integrating, that means you are performing this operation. As it is an indefinite integral, in the first step only you have to give this arbitrary constant and mention it is an arbitrary constant. Okay, Achha. So v square equals to this quantity. So obviously as v square we need is real, as v is real, because v is nothing but velocity, so there is no question of imaginary quantity or complex number. So v square obviously is real, so in that case c is positive. Okay, now why c is positive? Because you are saying it is an arbitrary constant, that means it can be arbitrarily large. That means if I do not consider c to be positive and I consider c to be a very large negative number, or then if you consider a large negative number, what will happen? It will become negative, and in that case v square negative. That means v complex number, that is imaginary, which cannot be the case because it is a velocity. So obviously c should be positive, that means it is an arbitrary positive constant. Okay, so now we are assuming some specific value of this c. Why suddenly this value? Let me mention it here only, though it will become clear after a few minutes. What actually we are trying to do here, we are trying to solve this simple harmonic motion. Simple harmonic motion, these two criteria we have already specified. Now in simple harmonic motion, what actually happens, there is a range of the distance over which the particle goes on moving. What actually happens here, let us just see the dynamics for a time being, then we will go back to the differential equation. So O is a fixed point. Suppose your particle was initial, that means at t equal to 0, when it has not started moving, it was at A. Okay, all of a sudden a blow is given to it and an external force starts acting on it, such that the external force is pulling the particle towards O. Okay, so what will happen? The particle will go on moving. shifting like this towards O. Okay, so as soon as it goes on moving towards O, it will at some time it will come at O. In the next time it will just cross O and go off to the other side, and we again go on moving and moving towards this side. But as it is simple running motion, so as soon as it starts moving on this left hand side of O, what will happen? The external force is pulling it towards O, so it cannot move for infinite time or for infinite distance, because whenever it is moving, its acceleration will go on decreasing because of this pull. So what will happen? After some time it will stop again, so that point is indicated at A dashed. So A was initial point from where it started moving. So whenever it was pulled towards O, what is actually happening? Its acceleration is going on increasing because it is pulled towards O, quite obviously. And as soon as it crosses O and moves towards the other side, it is pulled in the opposite direction. So its acceleration will go on decreasing, and after some time it will stop, and that point where it will stop is indicated at A dashed. P dash is any arbitrary instant of time position. Okay. So at A dash it will momentarily comes to rest. That means dxdt at that point will be 0. That means there will be no velocity, but still the particle is pulled. Okay, so because of this pulling, it will revert back its journey. After reaching A dash, it will not move in any further in this direction. It will not move across A dash. What will it happen? At A dash, it will take a U-turn. It will start moving again in this direction because of this pull. So as soon as it starts here, it is moving in the direction of the force. So again its acceleration increases gradually and gradually. So at O again it will cross O, and as soon as it crosses O, it is now moving in this direction, but the pull is in this direction. So again there is a mismatch in the pull's direction and the direction of the external force. So again its acceleration will go on decreasing as it moves along. So after some time it will again come to rest, and it will come to rest at the point from where it has started. So it started its journey from A, moved to O, crossed O, moved to A dash, then reverted back at A dash, again came to O, and ultimately it came to A. So starting from A and coming back to A indicates one complete cycle of the simple harmonic motion. And actually after coming to O, again what will happen? It will momentarily be at with velocity 0, but again the pull is as acting on it, so again it will start moving, and this will continue until and unless there is no resistive force decreasing this external force. So here we are considering the simple case of simple harmonic motion where there is no damping force. If there is a damping force, then what it actually naturally happens in reality it happens is this external force decreases in magnitude with time. Okay, so this cannot go on infinitely, but whatever we are doing here, this motion is going to occur infinitely. That means it starts at O, starts at A, crosses O, goes to A dash, then again reverts back, come to O, go to A, and then again starts moving, and this goes on as long as this force is acting. So this is a simple harmonic motion, the simplest form of simple harmonic motion. So this is going to continue again and again. Okay. Achha. So here we are trying to find out the complete cycle. The complete cycle of the simple harmonic motion, the time period, the time required to cover one complete cycle of the simple harmonic motion is referred to as a time period. Okay, so once you have the time period capital T, from there you can calculate the frequency of oscillation also, which is 1 by T. We will see one after another how we calculate this. So our main motive is to find all those quantities so as to specify the simple harmonic motion. Okay, so for that reason, what they are doing here, they solve it, and they are here taking C equal to mu A square, where A is nothing but OA length, this length, the initial distance. So if this takes C equal to this thing, then you can just simply put it here, and V square equal to comes to this thing. So V equals to V square, here you see V square equal to dxdt whole square equal to this quantity. So plus minus both of them are considered here. Okay. So once we consider that, plus minus both considered here. Why? Because we are considering this part of motion and this part of the motion together. Okay, so in some part it can be plus, in some part it can be minus. So as a whole, we are considering both plus and minus here. Okay, so this thing. So if you just integrate, obviously, then again another the arbitrary constant will come, and you are going to get this as your solution. Acha. First and foremost of all, what we can say from equation 5 is that what is the modulus of mod x is mod of this quantity, but cos is a bounded function, that means less than equal to 1 is the value, so mod x is less than equal to mod a. Now you see why we have suddenly taken this c equal to of this form. So as I said, it is whenever we are performing a simple learning motion, it is going to run over a specific range. That range is this value a. So mod x is less than equal to mod a. Distance on the particle cannot exceed the quantity a. Okay, on both sides of the fixed point. So at x equals to plus minus a, for plus a you are getting a, and minus a, that means x equals to negative coordinate, you are getting a dashed. And at this point, what will be your value of dx dt? The velocity vanishes at these 2 points. As I said, it will momentarily come to halt or momentarily come to rest. Rest means there is no velocity. That means dx dt is 0. When it will come to rest? At a and a dashed. Okay. The velocity vanishes, and at x equals to 0, the magnitude of the velocity is a root mu, which is maximum. Okay. Achha. Now, velocity vanishes, you can check from here also, because dx dt is what? Sine will come. Okay, so dx dt equal to 0 means from here only you can get, whenever we put a here, these quantities dx dt you consider from here, dx dt equal to 0 will ultimately give you, if for x equals to a or x equals to minus a, you are going to get this dx dt equals to 0. That means these 2 points. And at x equals to 0, that means at the origin, the velocity is maximum. This means a root mu. Okay, now let us start from here. So another term, this distance, this OA distance, this this much, this one is often referred to as the amplitude of the simple harmonic motion. That is the maximum range over which it can move on one side of the fixed point is said to be the amplitude of the simple harmonic motion. Okay. Now once we have got that, we will try to find out the time. There is a time period, as I said, to complete one full oscillation. So how can we calculate the total time period? First and foremost of all, let me just give an or focus on this figure once again. So what is the time period? As I said, starting from O and starting from A and coming back to A, the total time required for that journey. A, you start, go like this, come back to A, you complete one full journey or one full oscillation. It is said to be one full oscillation. What is the time required for one full oscillation? Achha. So actually this journey can be broken into some equal parts. From A to O, one part. Then again, due to symmetry, you see this is the whatever distance it is covered here, the same distance will be covered here also. It is a symmetric motion. Okay. So what time you require to move from A to O is the same as if you move from O to A dashed. Why? Because we have just seen that is the equation of motion is exactly the same if you consider on the right hand side of O or on the left hand side of O. So you will get exactly the same quantities. So the time you require to move from O to A is the same is the time you require to move from O to A dashed. Achha. Now once you do that, now when you are just coming back, again the time you require to move from A dash to O is the same, and then from O to A is again the same. So what we see, once you can find out the time to reach from A to O, you have to multiply it 4 times. Then only you will get the total time period. See, if I say is this time to be T1, if required to move from A to O, then 4 T1 is our time period. So exactly this thing will be done here. So we will try to find out the T1 only. Okay. So let us come back here. So, and x equals to a, let the particle be at a. When it is at a, let it give the time t0. T0 means initial time. Okay. T0 in general, it is considered to be 0 because initial time means what? You are not counting the time actually. So it should be 0. But here in mode specifically, they are taking it to be as notation T0. Okay. And subsequently at O, what is the time? T0 was an initial time. and you are taking some time to move from A to O, that means T0 plus T dash. That means some time you are taking to move from A to O. So if T0 is 0 also, you are taking the time T dash. Okay. So when you are, when if you focus on your differential equation solution, what you have obtained, there are two parameters, x and t. So if I take t0, then it is x equals to a, because you are at the position a. If you take t0 plus t dash, you are at the origin, that means x equals to 0. So using these two, we will give some calculations here. Okay. So that's what they are doing here. X equals to a when t equal to t0, and x equals to 0 when t equal to this quantity. So you just put it here and you just get this quantity. Just simple, just put this and you get these things. Okay. And here you just get this one from the putting x equals to a and t equal to t0, and again using this one you get this thing. Because if this is a solution, then definitely it is going to satisfy any position you take at any time you take for the whole journey of the simple harmonic motion. So I can put the point A, I can put the origin, I can put any intermediate point. Similarly, I can put the corresponding timing also, so I can calculate it. Okay, that's what they are doing here. They are using two values and finding out these quantities. So ultimately, you are getting t dash equal to this. This calculation is very obvious. You just go through it and you can have the idea how t dash is coming. Okay. So as I said, we are in search of this t dash. But why we are in search of t dash? Because t dash is the time required to move from A to O. And as soon as you get this t dash, as I already said, motion of the particle is symmetrical about O. Time required to move from A to A dash is this thing only. That means, as I have said, you are getting the same equation of motion. So whatever timing you are getting here, the same timing will be required here for going and again for coming. Okay. So 4 into t dash is our time period, capital T. So this thing, 4 into t dash. So this thing. Okay. Achha. Now some nomenclature. There is some notation or some name you have to keep in mind. The fixed point O is called the center of attraction or the center of oscillation. Maximum displacement A on either side of the center of attraction is called the amplitude of the oscillation, as I already said. And the simple harmonic motion is just said to be oscillation. Simple harmonic oscillation is the main or standard thing. Okay, another thing, if you just want to focus also, you just can have in your mind, you are getting a solution in the cosine form. Okay, and as we know, or we if you just consider the graph of the cosine function, how it goes on just like a undulation. It goes on rising and then again falls, and it goes on like this. If you just recollect back what is the form of this cosine function. So exactly the same thing is occurring in the dynamics also. As I said, you start from here, you go here, and again you come back, and again you go on, and so this whole thing is one full oscillation of the cosine function, and again another full oscillation of the cosine function, and this goes on. So that is also justification why this type of solution is coming here. When the motion is repetitive, obviously we should get a trigonometric cosine or sine function. Okay. Now once you get this, another thing, just a simple thing I have to mention here, that is the epoch. The angular frequency is nothing, as I said, if you cover n number of complete oscillations per unit time, that is the frequency, then n is nothing but 1 by time period. So this is the thing, because p we have already calculated, you can just simply say this is coming. Okay. Achha, now the quantity epsilon. What was actually epsilon in mathematical terms? It was an arbitrary constant. Whenever we did the integration for the second time, epsilon came as an arbitrary constant. But what is its physical related? How is it related to the physical scenario? It is called the epoch of this simple harmonic motion, and the angle root over mu t plus epsilon is called the argument. So this is coming in the cosine of this thing is coming, right? X equals to cosine root over mu t plus epsilon. So this is our argument. Obviously the angle we mean. Okay, and this is the epoch. Okay, so how this epoch is used? Actually this is used to calculate the phase. So the interval between any time instant t and the time when the particle was at its maximum distance, that is the amplitude, in the positive direction of the center of oscillation, that is the time required to move from A to P, is called the phase. So let us go back to the figure once again. So suppose you are at just catching the particle at any specific instant of time t, and corresponding position is P. Okay, but you have started the maximum distance, you have started at A, So the time required to move from A to P is set to the phase. And to determine this phase, this epoch will be used. Okay. Let's just only calculation you can see here. So the particle starting at A, be at A, what was the time? We are considered T equal to T0. Then the phase at P is T minus T0, because what is phase, as I already said? Time required to move from A to P. So it is a time. So if when my particle is at P, I am considering the time to be just T, time T equal to T. You can consider the T equal to T dashed. Then what is the time required to move from A to P? T0 minus T dash minus T0, because T dash is obviously greater than T0. You started from A, if it was at time say 5 seconds, then you have to move from A to P, definitely it will be greater than 5 seconds. So T minus T0 is the phase of the particle at the point P. So T minus T0 is this thing, but T0 you just simply can get from here, you just use it here. Okay, so you are getting this quantity. See here epsilon is coming. So the phase depends on this epsilon. It is epoch. Okay, and this is argument, as I already said. So argument by root mu is your phase at the point P. Okay. Now this was the whole picture of the simple harmonic motion, the theory behind the simple harmonic motion, and now let us do a few problems on this. Mainly the simple harmonic motion. That means the main thing is that the repulsive force, attractive force will be acting here. Maybe the repulsive force depends on the problem which is given. Okay. Achha, for doing any problem in the particle dynamics, not only this motion in one line or whatever, in whatever problem, whatever we will do through our course, one thing you have to keep in mind, whenever the question is given, please try to read it properly, so that you get the information which are given there. Once you get the information, we will use it to draw the figure, to sketch our reference frame. That means what will be the fixed point, what will be the fixed lines. Okay, what will be the initial velocity, what will be the uh, initial starting point. All this we will get from the problem itself. Okay, so whenever any problem is given, we will try to sort out the information one by one, then draw the figure, then do the reference frame, and then go to the equation of motion. Okay. So first let us read this question. A particle of mass m moves in a straight line under an attractive force. This is the attractive force. So as I said at the very beginning, it will be a function of the distance. Say m square x. So this is the magnitude. Okay. Then comes the direction towards the fixed point on the line when at a distance x from it. So as we can say, kx is the distance from the fixed point on the line. So it is, now this is the first part. Then what is said, it is projected with a velocity v towards the center of force from the initial distance a from it. Okay, so this is another piece of information. So what is the information is given? It is projected with the velocity v. So whenever it is starting its journey at the initial, at some initial point, it is not starting from rest. It is starting with some velocity. And what is the value of this velocity? Capital V. And this is the magnitude. And what is the direction? It is towards the center of the force. Okay. Achha. And what is the initial distance? A. So as I said, once you read the question, all the information will be provided there. Now comes what is the problem we have to do? Prove that it reaches the center of the force in this time. Okay, that means when x equals to 0, what is the time? You have to find that out. Okay. So before we start, one thing which I just say here, though in the book they have just simply started like this, but you cannot do it in your exam. As I said, you have to give a figure, you have to give your reference frame, all the specification, and then you have to start with the equation of motion. Whoever starts like this, obviously marks, there are part marking, and the corresponding marks for the figure, for the reference frame, and everything will be deducted. Okay, so please keep that in mind. So first let me just focus on the figure. So this is the figure you be giving. I'm not saying exactly this figure, but this type of figure you have to give, so that from the figure, whoever is doing the sum, the figure is related to the problem you are doing. So let fixed point O be considered as the origin as I said in the problem, there is some fixed point towards which the force is acting. So this fixed point will remain fixed throughout the problem we do. It will won't change. Okay. So let us consider that fixed point as our origin. We need one origin. So we have got the origin. Another one what we need an initial line. That means the x-axis we need. So that x-axis will be provided by the line over which the particle is moving, along which you are measuring the distance. So fixed point O considers the origin. Let the direction of the distance from O increasing, that is the direction of distance increasing from O, be considered as the initial line OX. So this is our figure, O fixed point. I have just again a typo here, capital X should be written along with the arrow sign. Again I am repeating here to give an arrow sign along with the capital X, just give as you draw the x-axis or the initial line. Okay, so this thing along with this writing should be mentioned here. After that, what you have to do, they have said small a is the length of the initial distance. So A is my initial point, O is initial distance. You have to write this. OP distance at any time t. Again, you have to write this and show it in figure as I have shown it here. Capital small x is a at any time t, so it's a running variable. This is a fixed quantity, so small a whatever is given in the question. And mn square x, you have to show the external force. Please do not forget to show it. And capital V is the projection velocity. Okay, so all these things we have to mention before you start writing the equation of motion. Acha, law of motion given by this thing. Acha, negative sign of for attractive force. As I said, you have to justify why you are putting negative sign. You just put negative sign without any justification, obviously will result in just reduction of marks. Okay, acha. Then you will just show, just see here, then calculation, you get something of this sort. Then again this minus sign I have to take. Okay, obviously they will be mentioning there. Achha, let me just go back to the sum, because whatever we have to write at the beginning of the sum, from here all these things up to here. Okay, this thing you have to mention. Now let us go back to the sum. Okay, so the see all those steps were jumped here. So I have mentioned it separately so that you can get a clear idea how to write the sum. Okay, so this is this thing. Then you go on just doing this integration. I am not going into these calculations again because you all know this thing now. Initially the arbitrary constant is coming, we have to remove it. So initially at t equal to 0, x equals to a, because initial distance was a. So once you do this thing, and v equals to minus v, because why minus v? Again, because it is projected towards the point. But what is small v? Small v is dx dt, and dx dt is increasing in this direction. Dx dt increasing in this direction, but your v is in opposite direction. So dx dt equals to minus v. Dx dt means small v, that is the running coordinate or running variable. So small v equals to minus v. See here, minus v is taken. Okay. So using all these specifications, you get the capital C here. You just use it, and ultimately you get this thing, and then you just small v equal to this, and minus is taken. They have also specified it here, and you have to specify why negative sign is taken, since the velocity is towards the fixed point and dx dt is towards x increasing, as I already said. Okay. So again from here you have to just integrate once again. Once you integrate, Achha. In the last integration, instead of considering it as an indefinite integral and then putting some specific value to find out the required quantity t, what we are doing, you are just directly framing it as a definite integral. Quite obviously, what you are doing here, dt equal to a function of x. Then we are integrating. What is the range of integration taken and why it is taken? 0 to capital T. Once you put this thing, we have to mention what is your capital T here, where t, capital T, is the required time from x equals to a to x equals to 0. This is what we are required or asked for, right? What will be the time required to move from the initial point to the fixed point? So this is the time. Okay. Acha. Corresponding limits on x will be what? Whenever we are starting from initial position, that means when t equal to 0, then you are at capital A. That means you are at a distance small a. Okay, and when you reach here, there is no distance from O. You are on O itself, so 0. So obviously these limits are quite justified. Minus sign already justified, and you perform the integration and find out the result. Okay. and you will see this is result is coming. And I will request you, please do this calculation on your own, okay, because it seems very easy, but whenever you are doing in the exam, it may become a bit non-trivial while in the intermediates. So it will be better if you just practice it on your own. Okay. Achha. So this sum is done, and this one said a particle moves towards the center of force O, the acceleration at a distance x from O being n square x, starting from rest at a distance a from O. When at a distance this from O, the particle receives the velocity na from O. Achha. So that, but this is the problem which is asked for. Let us keep it aside. Let us read this problem again. A particle moves towards the center of force O. Okay. Achha. The acceleration at a distance x from O being this. So the magnitude of the acceleration is given, starting from rest at a distance a from O. Okay. So what does it indicate? See here, it is not said that the acceleration is directed towards O, but it is said in the some other sense, but the same thing is said. See why they are saying starting from rest at a distance a from O. So the particle initially was at a distance a from O. Initially it was sitting there, and then it started moving towards O. Why it suddenly started moving? Definitely some force has been acted over here, has been put over there, that particle. So definitely the nature of the force is a pulling one. It is pulling the particle towards O. That's why the particle is moving towards O. Okay. So the nature of the force is again attractive. So now you see, in the, if you compare it with the previous problem, directly in the previous problem they said it was an attractive force, but here they are not saying directly it is an attractive force, but they are giving some other information from which you have to understand if the force is attractive nature. So that's why reading the problem is very crucial. You have to read it so that to get an idea what is the nature of the force, whether it is attracting or it is whether it is pulling the particle towards the fixed point or it is pushing the particle away from the fixed point. Okay. So this is the thing. Let me just show the figure first. So this one is the thing. So O is again the fixed point. As I said, I need a fixed point to act as the origin and an initial line for measuring the distance as the x-axis. So again, as I have written in the previous problem, here also you have to write the fixed point. Let us consider the center of force. It is given in the, this point is given already in the sum. What you have to write, let this be considered as the origin, as I have already written in the previous problem. Okay, I have not repeated it here. You have to write as I have written in the previous problem. Let this be considered the origin, and let OX, the direction of x in distance increasing from O, be considered as the initial line. This you have to mention just as I have mentioned in the previous problem. Okay, and please give an arrow sign here and put a capital X. That is the only typo which is there in this figure. You have to put a capital sign, capital X, and an arrow sign, so that to indicate that your x is increasing in this direction. Okay. And equation of motion d2 equals to minus n square x. Again, you have to justify minus because the force is attractive in nature. That also you have to write here. I am not repeatedly writing it here because I have already specified all this in the previous problem. Just like that, you have to write it again here. Why this negative sign is being put in this here. Okay. So it is an attractive force problem. That is quite clear. Achha. Now let us read the next half of the problem. When at a distance this a root 3 by 2 from O, something is happening to the particle. What is happening? The particle receives a velocity na from O. So what is it happening actually? The particle has started from an initial distance and it was moving under this force. Okay, till this distance it was all right, it was moving just like that. But at this one, something special has happened to the particle. Another velocity has been given on the particle, velocity of this magnitude from O. That means from O means what? What is the direction of the velocity given? In this direction the velocity is given. From O it is given, not towards O, but from O it is given. So the velocity that is in the NA is in this direction. That is in the direction of dxdt increasing. Okay, let us have the idea. Achha. Achha. So where it is occurring? When the particles, so the particle started from it was moving like this. All of a sudden at A dash it receives a blow from O, so that its velocity is given an amount na. So whatever, say suppose it was having a velocity v dash, it will now become v dash plus na. Okay, so that is the thing which will happen because of this sudden change at the point a dash. Okay. Acha. So actually because of this blow, what will actually happen, this whole equation, differential equation, will break up into two parts. First, you start from a, and before a dash one equation of motion, and again from a dash as something extra is happening to the particle, from a dash up to O, again another equation of motion. It may happen that the two equation of motions are the same, but we have to deal them separately. We have to treat them separately. We have to treat them as separate equation, and we have to carry on the problem. Okay. Because of the sudden change which is given here. If you compare it with the previous sum, there was no sudden change like this given. Only it was projected with an initial velocity. Initial velocity will not give any sudden change in the intermediate steps. You are only starting with the velocity, that is something different. But here in the midpoint, something is happening. Okay, as a result of which the equation of motion may change. Okay. So now let us see what they are doing. So this is the equation of motion. Before this, whatever we have to write, I have already specified. Achha. Then again, as you have done here, you are doing it here also. Achha. Now initially, so these are arbitrary constants. So these are all the same thing again and again. You have to do in a particle dynamics of particle. Okay, so t equal to 0, x dot 0. Achha, why x dot 0? This is also crucial. You have to understand it from the problem given. What is this given? A particle moves towards the center, the acceleration, and this, or starting from rest. So this indicates his initial velocity is 0. If you compare with the previous problem, the initial velocity was not 0 there because we projected it with the capital V. But here the particle is starting from rest. So at t equal to 0, that means at x equals to a, what is my dx dt? It is 0. So this is used here, you see, x dot 0. So you put it here, you find out C, all you put it together, you get x dot equal to this thing. So this is your x dot. Now at the special case, at x equals to this, what will be my x dot? You just put all thing here. So x dot is this thing. Now let me just remind you one thing. If there was no sudden change at this point, suppose this part was not given in the sum, what will be my velocity in that case? My velocity in that case at this point will be this thing. But here in the problem, they are giving something extra. They are saying the velocity will be added to the particle from O. That means my velocity, the normal velocity, that means this velocity of the particle will change. By what amount? By NA, this amount. So, they have written, and at this stage, the particle receives the velocity NA. Okay. As I said, now you see the equation of motion, I have to consider again. Since acceleration remains same, from 1 we get this thing. My x dot square equal to this thing, where c dash is another arbitrary constant whose value is to be determined from the conditions. Okay. Achha. So how I am getting this? Actually, I am getting this by solving again the differential equation, this thing. As I said, as it is receiving something extra in the intermediate step, again the equation of motion we have to be considered. But what is the equation of motion? How I have to consider the equation of motion? See, whenever it is said, suddenly it is receiving a velocity. But if it is receiving a velocity, this acceleration is not changing. This acceleration is still under the attractive force. That means it's still under this law of action or law of force. So its equation of motion will remain this only. So if you solve it again, what you will get? This thing only will get. But here I will write c dash. Why c dash? Because exactly that same arbitrary constant may not come. Some other arbitrary constant will come. And that arbitrary constant has to be you just find out, or has to be calculated using the sudden velocity which is added. Okay. So they are saying at this stage the particle receives velocity, but acceleration does not change. So you are getting this thing. Okay. The c dash is another arbitrary constant whose value is to be determined from the conditions. So what is the condition now? X dot is half na plus na. This plus na is because of the velocity which it is receiving. So you see, from the first half of the equation of motion, x dot is this thing. as it is getting an extra velocity, so the equation of motion is changing. You are, as the acceleration is not changing, you are getting this x dot only. But x dot at the specific point, this x equals to this is half na plus na because of the problem given. So it is this thing. So once you get this thing at x equals, so x is this thing, x dot this thing, you put all this here, you get c dash. So c dash is calculated in this quantity. So you just put it here and you get this x dot is equal to this one. Okay. So your ultimate x dot is this thing, keeping in mind whatever blow or whatever velocity it is giving. Okay, from the origin. Okay. Achha. Now this is the thing. Hence the new amplitude of the simplifying motion after receiving the velocity na is root 3a. Amplitude means what? Maximum distance. So maximum distance is what here? X, maximum distance is the distance where what will happen? The velocity will vanish. That means the particle will again come to rest. That means x dot will equate to 0. So x dot equal to 0, if I put here, I can find out this quantity x equals to root 3a. Okay, so this is my amplitude. Okay. Achha. So whatever this question was asked for, let me just recall back it once again. Achha. Show that the new amplitude of the oscillation is this thing. So this is actually what is asked for. We have to show the amplitude of the oscillation is this thing. So we have already proved it here. It is the thing coming. Okay. So this is it. Achha. Now here also for the here we are considering another type of motion. This is not simple harmonic, but it is motion under inverse square law. The same thing, only the external force will change, expression will change. But there was the external force for simple motion, it was directly proportional to the distance from the origin. So mu x was taken, mu being the proportionality constant. But here what will be the scenario? Inverse square law. That means it will be inversely proportional to the square of the distance. Inversely means 1 by x square. Okay. So this is the scenario, or this is a figure. Again, the fixed point or center of force is this thing. A is the initial point, starting point. OX is your initial line. P is at any time t position of the particle, and this is the law of force, mu by x square. Okay, so this is the equation of motion. Again, you have to solve like this. So once you solve like this, at the particle starts from, if it starts from rest, then obviously at OA equals to A, dx dt equal to 0. So putting all this, you can get back C. Okay, so once you get back C, you can just put it all together so as to get dx dt equals to whole square equal to this. Now dx dt equals to minus, again minus sign taken, you have to justify again the same justification. Ki negative sign is taken on the right hand side because the particle moves towards O, while dx dt is along OX, or dx dt is increasing along OX. So once you take that, you take the minus sign, again you can just integrate it so as to find out. Achha, plus d, again arbitrary constant will come. Achha. To evaluate the integral, they are just taking some specific substitution, this substitution, so as to solve this out. Achha, initially at t equal to 0, x equals to a, that is the I should not say amplitude, because amplitude is a specific term related to simple harmonic motion, but this motion is not simple harmonic motion, so let us say the initial distance. So x equals to a. So once you use it, you can find out the t. Okay. Achha. So from there only you can just equation 3 and 5 give respectively the velocity at the and the time at any point p of this path when x greater than 0. Okay. So from here only you can get the velocity. From 3, the velocity at O, that means the center of force is infinite. You can just simply see from here. Okay. Achha. And the time required to arrive at O is given by this. Obviously, if you put here this x equals to 0, dx dt, now equation 3, right? From here you can see as x is in the denominator, so obviously this dx dt will be infinite. What does it mean physically? Whenever it will reach the center of force, it is having infinite velocity. Actually, it is not realistically possible because of the fact that whenever this law of force will be acting, some resistive force will also be acting on it, which will decrease the magnitude of the force, as a result of which the velocity will actually not be infinite. But whatever, you just leave it behind. according to the problem or according to the calculation, at x equals to 0, that is at the center of force, your velocity is going to be infinite. Acha. Now, what will be the time you require to arrive at O? That can be given from here, because you put x equals to 0 here, you get the time. So this is the time. Achha. Next, let us consider the motion of the particle for x less than 0. Simply just you have to now consider this half of the motion. For this of the motion, again the same thing as I said here. Achha, mu by minus x whole square, right? So mu by x square only. Okay, but there will be plus sign because here particle is moving in this direction. So d2 dt2 should be plus mu x square, mu by x square. Okay, let us see it here. See, x double dot, that means d2 dt2 equals to plus, no minus. Why no minus? Because you are moving in the direction of x increasing. Once you are on this half of the axis, you are moving in this direction. Okay, but x is negative because of the negative coordinate, but there is whole square, so this minus will be absorbed there. So you get d2 as dt2 equals to mu by x square. Okay, so unlike the SHM, that is simple line motion, that equation of motion is changing on the two side of O. In simple line motion, ultimately we were getting the same differential equation or the equation of motion, but here it is changing. Okay, because in simple line motion there was mu x, so the negative coordinate was adding the minus sign. Okay, but here that is not occurring. So whatever, if I get another equation of motion, we will solve it. Okay, so as to find out. But since on the left side of O on OX, acceleration already related towards the velocity will diminish at the same rate as it was increased on the right side of O. Okay, and by symmetry, the particle will come to rest at O dashed. Okay, again at A dashed, the particle has no velocity but it has an acceleration, and ultimately it will again try to move towards O and it will retrace this path. So actually the same thing will go on happening. Just as we have encountered in simple motion, here also the repetitive thing will come. It will go, once it cross, it is trying to move in that direction, but the particle is pulled in this direction, so ultimately it has to stop at some place. It is stopping at A dash, and then it is retracing or reverting back, coming back from A dash, just as it happened in SHM. And again, while it is coming back, ultimately it will reach at O with infinite velocity. It will cross O again, it will start moving in this direction, but it is, while it is starting to move in this direction, it is pulled back in this direction, so that ultimately it will go on decreasing with velocity, and it will come to rest at A. So again and again this will go on as it went on in the same way in simple harmonic motion. Okay, so this is the case here. Okay, so here also that in the same way we can find